Okay, let's unpack this. When most of us think about AI, what springs to mind? Probably chatbots, maybe image generators, algorithms crunching data in some vast invisible cloud. It feels, very digital, very abstract. But what if that's only part of the story? What if the next great leap in intelligence isn't just about processing more information, but about having a physical presence? What if true intelligence, the kind that can genuinely understand and interact with our messy, unpredictable physical world, actually needs to be able to reach out and touch it?
That's precisely where the focus of, a lot of cutting-edge research is shifting now. We're talking about embodied AI. These are intelligent systems that aren't just running algorithms on a server somewhere. They're integrated directly into a physical form. Could be a robot, a drone, maybe something entirely new. And the key thing is, these aren't simply machines with some AI inside them. They are AI that is the machine, learning through direct, real-time consequences of physical action. It's a fundamental shift, really, moving intelligence from the purely abstract into the concrete.
Right. So our mission today is to take a deep dive into this whole unfolding revolution. We're going to explore what embodied AI truly entails and try to unravel why having a body is increasingly seen as, absolutely crucial for advanced intelligence. We'll also journey back a bit, trace its surprisingly long conceptual history. Then we'll dissect the intricate hardware and the sophisticated software that empower these agents to move and, think. We'll showcase some incredible breakthroughs happening right now. I mean, we're talking humanoids already being tested in factories, and delve into their immediate and future impact on everything from global logistics to elder care. And finally, we have to confront the significant challenges and the profound societal questions this revolution inevitably brings. So this deep dive is really your shortcut to understanding a transformation that's not coming. It's already reshaping our world.
Exactly. And to really get what embodied AI represents, we need to grasp that the world of artificial intelligence is actually kind of splitting. It's heading down two fundamentally different paths, two ways of thinking about what intelligence even is.
That's a powerful distinction. So on one side, we have what most of us are familiar with now, disembodied AI. Think large language models, right, like the ones we interact with online. These systems exist purely in abstract digital realms. They're essentially just data, logic, and language living on servers in huge data centers. They process absolutely gargantuan data sets, text, images, code, but they do it all without any physical form, without any direct, unmediated experience of the world they're describing. They just operate in that digital symbolic space.
And then the other path, you have embodied artificial intelligence. These are intelligent systems that inhabit physical or sometimes even simulated bodies. The core idea here is their ability to perceive, act upon, and crucially learn from their environment through direct real-time interaction. They gather live data through a whole suite of sensors, and this is key, they adapt their behavior based on the physical consequences of their actions. It's intelligence grounded in direct reality, not just abstract symbols.
So it's not just a technical difference in how they're built. It's really a fundamental divergence in how we even conceive of intelligence itself. The first path, this thought-first approach of disembodied AI, it's cognitive before it's physical. Its intelligence comes from analyzing massive archives of human knowledge, books, conversations, websites, code. These systems get really good at symbolic tasks like language processing, data prediction. They're kind of like incredibly knowledgeable oracles or philosophers operating within the framework of human-derived concepts. Their reasoning is, to some degree, sort of anchored to our conceptual world.
But the action-first path of embodied AI is starkly different. These agents begin with motion, not necessarily meaning. Think about it like a human infant exploring the world. They perceive their environment, they act within it, and they learn through direct physical feedback, success, failure, collision, balance. Their intelligence isn't preloaded from human archives. It actually emerges from continuous interaction with the messy, unpredictable physical world. A world shaped by physics, not philosophy. This means their learning process is deeply rooted in the same physical reality that we humans inhabit, making them something kind of parallel to us, not just an extension. And this trajectory shifts the whole conversation. Disembodied AI might offer partnership, but embodied AI, it could evolve more like a new species.
A new species. Wow, that's a powerful and, frankly, a bit unsettling idea. It fundamentally shifts how we think about what we're creating here, doesn't it? So if this action-first path is so profound, what's the core argument? Why is a body even necessary for a mind? This is the heart of what researchers call the embodiment hypothesis, right?
That's it. The central conviction, the core belief, is that a physical body isn't just an optional add-on for an intelligent mind. It's actually a fundamental prerequisite for developing robust, adaptable, and truly general intelligence. This hypothesis argues that cognition itself, thinking, emerges from this intricate dynamic synergy between, let's call it the brain, the body, and the environment they exist in.
So intelligence isn't just some abstract computation that you can divorce from physical form. That really challenges a lot of the traditional AI thinking.
It absolutely does. The hypothesis posits that a body's specific physical characteristics, its size, its shape, its sensors, its actuators, its muscles, they actively shape and constrain its cognitive processes. There's this phenomenon called morphological computation. It suggests that some of the information processing is actually offloaded to the physical structure of the body itself. It reduces the computational burden on the central brain. A great example is a soft robotic gripper. Its mechanical compliance, its softness, allows it to passively adapt to an object's shape. Trying to do that with a rigid gripper would require incredibly complex sensing and computation. So from this perspective, intelligence isn't located solely in an algorithm somewhere. It emerges from this continuous feedback loop between the agent's mind, its body, and the world.
And this embodied approach helps overcome some of those persistent limitations we see in disembodied AI, right? I've heard people talk about the symbol grounding problem. What's that about?
Ah, yes, that's a crucial one. Disembodied AIs learn primarily from language, which is a system of abstract symbols. So a large language model can process vast amounts of text about, say, an apple. It knows all the words associated with apples, but it has absolutely no direct sensory experience of what an apple actually is. Its weight, its texture, its smell, the sound it makes when it drops. Its knowledge is, in a sense, one layer out from actual experience. It's confined to the symbolic realm. And this can lead to a kind of shallow, brittle understanding. An embodied agent, by contrast, grounds the symbol apple in a rich, multimodal stream of sensory-motor data acquired by actually seeing, touching, maybe even manipulating one. This direct experience provides a much deeper, more robust foundation for knowledge.
Okay, so beyond grounding symbols like Apple, it also seems like disembodied AI struggles with the sheer unpredictability of the real world. Is it fair to say they're often quite brittle compared to an embodied agent?
That's a great way to put it, yeah. Brittle. Models trained purely on static data sets often just fall apart when faced with the noise and chaos of reality. An embodied agent, because it learns through direct interaction with this messy reality, is constantly subjected to what you could call a reality check. This process forces it to develop strategies that are resilient. Resilient to sensor noise, unexpected obstacles, constantly changing conditions. It fosters an adaptability that is incredibly difficult, maybe impossible to achieve through offline training alone.
So if we're really talking about building truly adaptable and generally intelligent systems, maybe something approaching artificial general intelligence, then embodiment isn't just a good idea, it's actually a critical step.
Many leading researchers now argue exactly that. That embodiment is critical, maybe even indispensable, for achieving artificial general intelligence, or AGI. Think about the definition of AGI. Capabilities like autonomous learning, adaptation to totally new environments, the ability to perform a broad range of different tasks. These are all hallmarks of embodied systems, not disembodied ones. True intelligence seems to require a causal understanding of the world, knowing why things happen. It needs the ability to dynamically revise beliefs based on experience and the capacity to actually execute actions in the physical realm. Disembodied models can simulate reasoning, sure, but embodied agents have to actually practice it in a world with real consequences. And this active, consequential learning, it's believed to be essential for the emergence of truly general intelligence.
It's really incredible to see how quickly this field is accelerating today. But what's also fascinating is that this isn't some brand new spark, is it? We're actually kind of reigniting a flame that's been burning in the minds of pioneers since the very dawn of computing. Let's maybe journey back a bit, understand where these profound ideas truly began.
Yeah, we're certainly witnessing a powerful return to ideas that have been discussed, debated, experimented with since the earliest days of computing. You know, the history of AI has actually been this kind of pendulum swing, back and forth between purely computational, disembodied philosophies and these interaction-centric embodied ones. The current revolution is really amplifying those embodied roots, but now with unprecedented computational power.
And did these early ideas about intelligence needing physical interaction go back as far as the very pioneers of computing, people like Turing?
They absolutely did. Think of Alan Turing himself. In his 1948 and 1950 papers, he explicitly speculated that creating a truly intelligent machine would probably require providing it with sensory organs and allowing it to learn through interaction with the world, much like how a child learns. These conceptual origins were then formalized in the 1940s and 50s with the emergence of cybernetics.
Right, cybernetics. And that's where the whole idea of the feedback loop comes from.
Precisely. Cybernetics was fundamentally the study of control and communication, both in animals and machines. Its central contribution was this concept of the feedback loop, the idea that an agent's actions affect its environment, and then information about that effect is fed back to the agent through its senses, allowing it to adjust its next actions. This established the core principle that intelligent behavior arises from this continuous interaction between an agent and its environment.
And the first actual physical embodied agents were those fascinating tortoises back in the 1950s.
Yes. William Gray Walter's tortoises, named Elmer and Elsie. These were really simple machines, built with just basic light and touch sensors connected directly to motors. The remarkable thing was, without any central processor, without any pre-programmed plan, they exhibited surprisingly complex, almost lifelike behaviors. They would explore their environment, they'd avoid obstacles, and they'd even navigate towards a light source to recharge their batteries when they got low. They were a powerful proof of concept that intelligent-seeming action could emerge just from simple sensor motor loops.
Okay, so after those early, simpler examples, it seems like the ambition grew, leading to something more complex, like Shaky the robot. What was Shaky's big contribution?
Shaky, developed at Stanford Research Institute in the late 1960s, was a really significant leap forward. It was the first mobile robot that could actually reason about its own actions in a symbolic way. It integrated a camera and touch sensors with a remote computer which housed a symbolic AI model of its world. Shaky operated using this sense-plan-act architecture. It would perceive the world, create a symbolic plan, and then try to execute it. But it was famously notoriously slow, sometimes taking hours just to process information and decide on its next move. And this really highlighted the brittleness, the inefficiency of purely symbolic approaches when you're faced with dynamic, real-world environments that change.
And that slowness, that brittleness,
Yeah.
it contributed to a period of disillusionment in AI, right? A period often called the AI winter, which then led to a kind of radical rethinking championed by people like Rodney Brooks.
That's right. Rodney Brooks, a roboticist at MIT, became a really pivotal figure during this period of questioning the dominant approach. In his seminal 1991 paper, Intelligence Without Representation, Brooks argued that this intense focus on complex internal models and symbolic reasoning was maybe misguided for robotics. He proposed a different approach called the subsumption architecture. Here, intelligent behavior emerges from a hierarchy of simple, layered behaviors that directly couple perception to action. So, for instance, a robot's lowest level behavior might just be avoid obstacles. A higher level behavior like wander operates on top of that, guiding the lower level. This behavior-based robotics approach, which he demonstrated in robots like his six-legged Genghis, showed that complex adaptive locomotion could be achieved without needing a centralized symbolic world model at all. And this work laid the direct intellectual foundation for a lot of modern embodied AI.
And this behavior shift, it wasn't just happening in robotics, right? It had echoes in cognitive science, too.
Absolutely. Philosophers and neuroscientists, people like Francisco Varela and Linda Smith, were reinforcing these ideas from different angles. They argued that human cognition itself isn't some abstract process happening separate from the body. It's deeply rooted in and actively shaped by the body's physical interactions with the world. This whole embodied perspective gained traction across multiple disciplines, really setting the stage for what we're seeing today.
Okay, here's where it gets really interesting and maybe a bit counterintuitive. The explosive success we've seen recently with disembodied large language models that's now powerfully fueling the embodiment revolution. How does that actually work?
Yeah, it is a fascinating and incredibly powerful synergy. Basically, large language models provide a readily available, off-the-shelf, and incredibly powerful cognitive engine. They handle language understanding and high-level reasoning extremely well. This solves a critical piece of the puzzle that robotics companies previously had to build entirely from scratch, which was hugely difficult. So now they can integrate these sophisticated reasoning capabilities into their embodied agents and focus their efforts, their resources, on the core challenges that are unique to embodiment. Things like robust perception in cluttered environments, dexterous motor control for complex manipulation, and, crucially, bridging that persistent gap between simulation and reality. This fusion, where disembodied cognitive power is integrated into physical bodies, really defines the current era. It allows robots to not just act based on simple rules, but to understand complex commands, generate detailed plans, and interact with humans in a far more sophisticated and, frankly, intuitive way.
Okay, so with that history lesson sort of setting the stage. Let's dive into the actual anatomy of an embodied agent. We're talking about this intricate interplay between its hardware, its physical body, and its digital cognition, its mind. It's like this complex synthesis, right?
Precisely. The physical corpus, the body, gives it existence and the ability to act in the real world, while the digital mind provides perception, learning, decision-making. And there's this powerful feedback loop happening here. Better hardware generates richer, more detailed data, which then demands more powerful AI models to process it, which in turn drives the need for even more dexterous and efficient hardware. It's a cycle.
Right. And first, the physical forms themselves. It's definitely not just humanoids anymore, is it? There's a whole spectrum of these embodied agents out there.
Oh yeah, absolutely. The physical manifestation of embodied AI is incredibly diverse. It's highly specialized depending on the operational environment and the tasks it needs to do. You have, of course, humanoid robots designed with a body like ours torso, 2 arms, 2 legs specifically to operate in environments built for humans, using human tools. Think Tesla Optimus or Figure 2, which are aimed at general-purpose tasks, initially maybe in manufacturing, but eventually in homes. Then there are the classic robotic arms and manipulators. These are the industrial workhorses, usually fixed in one location for high-precision tasks like welding or assembly. Companies like Kuke and Fanuc are big here. You have autonomous drones and vehicles designed for mobility and transport over large areas, things like aerial inspections, self-driving cars, those warehouse trucks you see. Quadrupeds, the 4-legged robots like Boston Dynamics Spot, are engineered for exceptional stability and mobility on uneven terrain. Really good for inspection or search and rescue. At the simpler end, you've got smart home devices like robotic vacuums and lawnmowers. They represent basic embodied intelligence navigating constrained home environments. And then there's this fascinating burgeoning class, soft robotics. These are built from compliant, flexible materials. They're inherently safer for human interaction and can adapt their shape to grasp delicate or irregularly shaped objects. Very promising for areas like healthcare and food handling.
Okay, so they have their bodies, specialized forms. But what are the muscles made of? How do they actually translate a digital command into physical movement?
That's a core engineering challenge, choosing the right muscles, which we call actuators. These are the components that convert energy, usually electrical, sometimes hydraulic or pneumatic, into physical motion. For the kind of precise, delicate movements you need in, say, a humanoid's fingers or a complex robotic arm, electric systems are generally preferred. They offer high precision and they're easy to control. But if you need immense power, raw force, maybe to lift heavy loads in a factory, or for a really large robot like some of the older Atlas models, you might still see powerful hydraulic systems that use pressurized fluid. They're incredibly strong, but they can be complex, potentially messy, and less precise. Then there are pneumatic actuators. They use compressed air for rapid motion. They're fast, simple, relatively lightweight, often used for quick pick-and-place tasks or in some types of soft robotics. But they offer less precise position control because air is compressible. So each choice involves trade-offs: precision versus force, cleanliness versus complexity. Understanding these choices tells you a lot about what a robot is designed to do.
Right, the actuators are the muscles. Right. But all that motion, plus all the onboard computing, that needs a lot of energy. What's the metabolism like for these embodied agents? Power is a big deal, I imagine.
It's huge. For true autonomy, being untethered is critical. And the onboard power system is very often the limiting factor. The main challenge is just storing enough energy in a compact, lightweight form to power these energy-hungry motors, the processors doing the AI work, and all the sensors, hopefully for an extended period. The field is currently dominated by lithium-ion battery chemistry and its variants, like LiPo or LiFePO4. They offer the best balance right now of energy density, power output, and rechargeability. For instance, the Tesla Optimus Gen 2 is designed with a 2.3 kilowatt-hour battery pack. The aim there is to get a full workday of operation, and just as crucial as the batteries themselves is managing them. A sophisticated battery management system, or BMS, is absolutely essential. It monitors the battery's health, protects against things like overcharging or overheating, and performs cell balancing to ensure a long, safe lifespan.
Okay, so they have their bodies, their muscles, their energy source. But to truly act intelligently, they need to perceive what's happening around them. How do these embodied agents actually see and feel the world?
Yeah, intelligent action is entirely dependent on perception. It's fundamental. Robots use a whole suite of sensors, and we can broadly categorize them into exteroceptive sensing the outside world and proprioceptive sensing the internal state of the robot itself. These are basically their windows to the world and their sense of self.
Let's start with how they perceive the outside. What are their windows?
Okay, so vision using cameras is a primary modality. just like for us. It provides rich, high-resolution data that's great for object recognition, understanding a scene, navigation. Now, a crucial distinction. Humans automatically apply context and understanding to what we see. A robot's computer vision system is fundamentally processing pixels, lines, shapes, colors. But robots do have an advantage. They can operate outside the human visible spectrum. They can use infrared or ultraviolet cameras to see heat signatures or other phenomena invisible to us. LiDAR, which stands for light detection and ranging, is also incredibly important, especially for navigation and spatial awareness. It emits laser pulses and measures the reflection time to generate these dense, highly accurate 3D point clouds of the environment. It's exceptionally effective for precise mapping and detecting obstacles, often more accurate for distance than cameras, though it can be more expensive and affected by things like fog or rain. And then for touch, advanced tactile sensors are becoming truly like the robot's skin. They can measure incredibly subtle forces, pressure, vibration, even texture. Imagine a robot needing to adjust its grip on a delicate object like an egg to avoid crushing it, or detecting if something is starting to slip from its grasp. That requires sophisticated touch. Some cutting-edge systems, like GelSight, even use tiny cameras inside a soft gel pad to see how the gel deforms under pressure, giving them a really rich, high-resolution sense of touch. Beyond these main ones, robots might use radar for robustness in bad weather, ultrasonic sensors for cheap, short-range proximity detection, or microphones for voice commands and listening to environmental sounds.
So they have eyes, a sophisticated sense of touch, maybe some hearing. But how do they know where their own body parts are, how they're moving? That's proprioception, you said.
Yes, proprioception is the robot's internal sense of self. It's awareness of its own body's configuration and movement in space. This internal feedback is absolutely fundamental for any kind of controlled motion. Encoders are probably the most common component here. They're typically attached directly to a motor shaft to measure its rotation very precisely. This tells the system the exact angle of a joint or maybe the distance a wheel has traveled. It's really the bedrock of precise, closed-loop motor control. Inertial measurement units, or IMUs, are compact little devices that combine accelerometers, measuring linear acceleration, and gyroscopes, measuring angular velocity. By integrating the data from these sensors, an IMU can track the robot's orientation, its pitch, roll, and yaw in its overall movement. They are absolutely critical for maintaining balance in legged robots like those Boston Dynamics ones, and also for stabilizing drone flight. And finally, you have force torque sensors. These can be placed within a robot's joints or at its end effector, its hand, to directly measure the forces and torques being applied or experienced. This information is vital for tasks that require precise force control, like maybe polishing a surface with consistent pressure, or for ensuring safety by detecting unexpected forces during human-robot interaction.
It's incredible the range of sensors they have and how differently they perceive compared to us. So the hardware, the body, is incredibly sophisticated. But it's just inert metal and plastic without a mind, right? What are the digital learning and reasoning architectures that bring it all to life?
That's exactly right. The digital mind of a modern embodied agent isn't just one single program. It's more like a layered architecture of interconnected software components. The field is kind of converging on a standard stack of technologies that all work together, and the foundational learning paradigm for most of these agents today is reinforcement learning, or RL.
And RL is essentially learning through trial and error, like we talked about with the baby learning to walk.
Precisely. RL is how an agent learns to make decisions. It performs actions in an environment, gets feedback in the form of a reward signal, positive for good actions, negative for bad ones, and tries to maximize its cumulative reward over time. So instead of being explicitly programmed with rules for every situation, the agent learns a policy, basically, a strategy for mapping situations to actions through this trial and error process. In robotics, this is extremely computationally intensive. It often requires millions, sometimes billions of interactions to learn a complex skill. Some key algorithms used here are proximal policy optimization, or PPO, which is valued for its stability, and soft actor critic SAC, which is known for being more sample efficient and balancing reward maximization with exploration.
Millions or billions of interactions in the real world. It
Yeah.
sounds prohibitively expensive and incredibly slow, not to mention risky. How do they deal with that?
That's exactly the problem, and it's where world models become absolutely crucial. Think about it this way. A child touches a hot stove once. They don't need to keep touching it hundreds of times to know it's hot, right? They've quickly built an internal model of how that part of the world works. That's essentially what a robot's world model does. It's an internal, learned simulation of its environment. It learns the physics and dynamics, how actions change the world from its past experiences. This allows the robot to mentally rehearse or imagine thousands, even millions, of potential actions and their consequences within its own digital mind without taking a single, potentially costly physical step. It's like having an internal simulator that helps it plan much more efficiently and enables sophisticated long-horizon planning thinking many steps ahead. Architectures like Google DeepMind's Dreamer series are influential here.
That's amazing. So the robot essentially develops a kind of imagination to help it plan, and then there's multimodal AI, which is about bringing all those diverse sensor inputs together, right? Vision, touch, sound.
Exactly. Embodied agents are inherently multimodal. They have to process and integrate information from all these diverse sensors, simultaneously vision, maybe language input, tactile feedback, proprioception, telling them where their limbs are. Multimodal AI models are specifically designed to fuse these disparate data streams into a single, cohesive representation of the world state. The most prominent examples in modern robotics, the ones getting a lot of attention, are vision language action, or VLA models. These models, often built on transformer architectures like LLMs, can take a natural language command like, "Please hand me the blue cup from the table," along with visual input from a camera, and translate that directly into a sequence of motor commands to actually execute the task. This fusion of language, vision, and action is what enables the fluid, intuitive human-robot interaction we're starting to see in recent demos, like from Figure AI.
And finally, sitting on top of all this, you mentioned cognitive architectures. What role do they play?
Right. Cognitive architectures provide a kind of high-level, principled framework for organizing all the components of an agent's mind perception, memory, attention, reasoning, action into a coherent functional system. They're often inspired by theories of human cognition and aim to provide a blueprint for achieving more general intelligence, not just excelling at one specific task. Classic examples include SOAR or ACTR. A really significant contemporary trend now is the fusion of these structured, perhaps more symbolic, cognitive architectures with the powerful general knowledge capabilities of generative models, like large language models. This hybrid approach aims to combine the benefits of explicit, interpretable reasoning and goal management from the cognitive architecture with the vast common sense world knowledge learned by an LLM from internet-scale data. The hope is this leads to agents that are both more capable and more understandable, maybe even safer.
Okay, that gives us a really solid grasp of the fundamental building blocks. Now let's pivot and look at the revolution in action, the breakthroughs, the real-world applications that are happening right now. And it definitely feels like the human form factor, humanoid robots, are really taking center stage here.
You're absolutely right. Humanoid robots have, captured imaginations for decades, but it's only very recently that they've become a focal point of serious commercial and technological investment. This surge we're seeing is driven by a kind of convergence. We have more powerful and efficient actuators, much more advanced AI, especially these large-scale models for perception and control, and also a strategic bet by major companies. The bet is that the humanoid form is ultimately the key to general-purpose automation in a world that's already built for humans. A robot with a human-like body can, at least in theory, use the same tools we use, navigate the same spaces, perform the same tasks, all without requiring a complete redesign of our existing infrastructure, factories, warehouses, maybe even homes. This makes the humanoid a potential sort of universal interface for interacting with the physical world.
And the competitive landscape seems to be heating up incredibly fast. Can you walk us through some of the key players and their recent developments? What's been happening in, say, the last year or two?
It's truly remarkable, the acceleration just in the past 24 months. Let's look at some of the leading platforms and recent updates, keeping in mind this field moves incredibly quickly. First, Tesla Optimus Gen 2. Tesla's approach is really defined by their vertical integration and this bold ambition for mass production. They're heavily leveraging the vast real-world data and the AI infrastructure they developed for their full self-driving program. This gives Optimus, potentially, a significant advantage in navigating and learning in complex, unstructured human environments. In recent demonstrations, we've seen Optimus performing tasks like sorting colored blocks, doing basic factory work. Tesla announced plans for test production starting in 2025. This latest version, Gen 2, also featured a significant 22-pound weight drop compared to the previous one and has impressively dexterous hands, making it seem more agile and capable. Then there's Boston Dynamics' Electric Atlas. They've long been the leader in dynamic locomotion, those amazing jumping and backflipping robots. But the new all-electric Atlas, which they unveiled in April 2024, is quite different. It's stronger, more dexterous, has much sleeker design. Crucially, the company is now shifting its focus away from those awe-inspiring acrobatics towards practical commercial applications. They have planned deployments in Hyundai's manufacturing facilities. Hyundai actually owns Boston Dynamics. And they also recently announced a partnership with LG Innotek to develop next-generation vision systems specifically for Atlas. AI's Figure O2 has emerged as a really formidable and fast-moving competitor. After an initial high-profile partnership with OpenAI, they went on to develop their own powerful Helix Vision Language Action VLA model in-house. This enables their robots to understand and perform tasks based on natural language commands. As of late 2024, Figure O2 is already being tested in a real-world industrial setting at a BMW manufacturing plant in South Carolina, performing logistics and handling tasks. And they're even running pilots with UPS for package handling. That's incredibly fast progress. Sanctuary AI's Phoenix takes a slightly different strategic path. They seem to be prioritizing the development of highly dexterous, human-like hands with advanced tactile sensing, perhaps even more than perfecting bipedal locomotion right now. Their bet seems to be that the immediate commercial value lies in a robot's ability to perform complex manipulation tasks that require fine motor skills. Their Phoenix robot uses a unique combination of human teleoperation for training and AI learning, aiming to fill labor gaps across a variety of industries. And Agility Robotics Digit. Digit represents a highly pragmatic approach focused on commercialization now. It's specifically optimized for a high-value task, moving totes around in logistics and warehouse environments. This focused strategy led to early deployments with major customers like Amazon, where Digit is being tested for handling tasks alongside human workers in their facilities. We're also seeing other players making significant strides, like PL Robotics from Spain, showcasing their humanoid platforms for diverse industrial tasks at major trade shows like Automatica 2025. So the market is definitely hitting an inflection point, with the World Economic Forum and others highlighting both the disruptive potential and the promise of these systems.
The pace is just stunning. So beyond these headline-grabbing humanoids, how else is embodied AI transforming industry and science right now? Where's the impact already being felt?
Well, manufacturing and logistics are definitely the primary beachhead markets today. The drive for efficiency, safety, and resilience against labor shortages is immense in these sectors. In smart warehouses, for example, autonomous mobile robots, AMRs for just transporting goods, are already commonplace. But now, more advanced bipedal robots like Agility's Digit are being tested by companies like Amazon for actually handling totes and other logistics tasks, showing how humanoids can integrate into spaces designed for people. We're also seeing a significant rise in collaborative robots, or cobots. These are typically robotic arms designed to work safely right alongside human workers, taking over repetitive or strenuous tasks, freeing up the humans for more complex problem solving and quality control. This is all part of a broader trend, sometimes called Industry 5.0. It's a paradigm that aims to move beyond pure automation towards a more human-centric approach, where intelligent cyber-physical systems collaborate with humans for more resilient, sustainable, and even personalized manufacturing processes. A concrete example. Foxconn, the giant electronics manufacturer, in partnership with NVIDIA, recently announced they began training robots on intricate assembly tasks that human workers currently repeat thousands of times a day on their production lines.
And outside the factory floor, what about scientific discovery? How are these embodied agents accelerating research?
Embodied AI is rapidly emerging as a powerful new kind of instrument for discovery. Automated experimentation is a huge area. Robots can perform laboratory experiments with superhuman precision and endurance, running 24 hours a day, 7 days a week. This can dramatically accelerate research in fields like materials science, drug discovery, biology. There was a notable breakthrough from a company called Explore Science. They developed an embodied AI system capable of autonomously conducting end-to-end psychology experiments. Everything from formulating hypotheses to recruiting human participants online and analyzing the data. That's quite a leap. They're also proving vital for the exploration of hazardous environments. Robots and drones are extending human senses into places we simply cannot safely go ourselves, whether it's exploring deep-sea hydrothermal vents, navigating the rubble of disaster zones to find survivors, inspecting critical infrastructure like pipelines or bridges, or serving as our proxies on the surfaces of the Moon and Mars.
It's not just impacting big industry and science labs, though. What about integration into our daily lives, and particularly healthcare?
Right. While the vision of a general-purpose humanoid robot doing chores in every home is still some way off, specialized embodied agents are definitely making their way into our daily lives. The most common forms of domestic embodied AI today are those specialized task robots, things like advanced robotic vacuums and lawnmowers. They use sensors and AI to navigate and map household environments effectively. But companies like Tesla are quite explicit about their long-term vision. They see their humanoid robots eventually transitioning from factory floors into homes to perform a much wider range of household chores.
And healthcare feels like an area where the impact is already profound and maybe growing fastest.
It truly is. Healthcare is seeing significant and growing impact. Surgical assistance is a prime example. Robotic systems, like the well-known Da Vinci surgical system, act as these highly precise master-slave embodied agents. They translate a surgeon's hand movements into micro-movements of tiny instruments inside a patient's body, enabling much more precise, less invasive procedures. Rehabilitation and assistive robotics are also transforming lives. We see robotic exoskeletons helping patients regain mobility after spinal cord injuries or strokes. And assistive robots are being developed to help elderly people and those with disabilities with daily tasks, things like lifting, fetching objects, moving around, promoting independence, and improving quality of life. Medical logistics and access to care have seen incredible impacts, especially with autonomous drones. Companies like Zipline are using drones to deliver blood, vaccines, and critical medical supplies to remote clinics, for instance, in Rwanda and Ghana. They dramatically reduce delivery times and are literally saving lives in areas with poor road infrastructure. And finally, there's this really interesting emerging field of companionship and mental health. Social robots are being developed specifically to address issues like loneliness and social isolation, particularly among the elderly population. Robots like LQ are designed to proactively engage with users, initiate conversations, suggest activities, serving as companions aimed at improving emotional well-being.
So we've covered the what, the why, the how, and the where this revolution is happening. But with all this incredibly rapid progress, there must be some major hurdles still, right?
Yeah.
What are the really critical challenges on the path to full, widespread embodiment?
Oh, absolutely. There are indeed formidable challenges remaining, and they are deeply interconnected. You could almost think of them as forming a complex trilemma. The three primary hurdles that researchers and engineers are constantly grappling with are, first, the gap between simulation and reality, second, the inherent physical limitations of hardware, and third, the profound difficulty of achieving true generalization and adaptability in robots. And the field seems to be shifting slightly from trying to perfectly solve these problems, which might be impossible, to finding clever ways to pragmatically manage their complexity.
Okay, let's start with that first one, the reality gap or the sim-to-real gap. It sounds like a really fundamental problem.
It is. It's arguably one of the biggest persistent challenges in all of robotics. The issue is, training these embodied agents, especially using data-hungry methods like reinforcement learning, directly in the real world is just impractical for most complex tasks. It's incredibly slow, it's very expensive, and it can easily damage the robot or its surroundings. Think of a robot learning to walk by falling over thousands of times, not ideal. So researchers rely heavily on physics-based simulators like NVIDIA's Isaac Sim or MuJoCo. But here's the rub. A policy, a learned behavior that performs flawlessly in the clean, predictable environment of a simulation often fails catastrophically, sometimes immediately, when transferred to a physical robot in the real world.
Why does that gap exist? Is it just that the simulations aren't perfectly accurate representations of reality?
That's a big part of it, yeah. It boils down to the immense difficulty of creating a perfect digital twin of the messy, complex physical world. Simulators are ultimately approximations. They struggle to perfectly model complex real-world physics, especially things like contact dynamics, how objects interact when they touch, friction between surfaces, or how soft, deformable objects behave. These are incredibly hard to simulate accurately. On top of the physics inaccuracies, real-world sensors have noise, they have calibration errors, they're affected by changing lighting conditions in ways that are hard to replicate perfectly. Physical components, like motors and actuators, have delays, they have friction, they have power fluctuations that are difficult to model with complete fidelity. And even subtle differences in visual appearance, textures, lighting, shadows between a simulated scene and its real-world counterpart can completely confuse a robot's vision system if it was trained only on synthetic images.
Wow, okay. So given that perfect simulation seems impossible, how are researchers and engineers trying to bridge this gap? How do you get simulated learning to transfer effectively?
The goal isn't necessarily perfect simulation anymore. It's shifted towards training a policy that is robust enough to be relatively insensitive to these inevitable differences between sim and real. A very widely used and successful technique is called domain randomization. Instead of trying to painstakingly model one specific set of real-world physics parameters during training in the simulator, they intentionally vary a wide range of these parameters, things like object textures, lighting conditions, friction coefficients, even the robot's own mass distribution. By exposing the AI to this wide distribution of possibilities during simulation training, it's forced to learn a policy that is robust enough to generalize reasonably well when it encounters the slightly different, messy reality. Another key approach involves using those world models we talked about. By allowing the robot to train extensively within its own learned mental simulation of the world, it naturally improves its ability to adapt to small discrepancies when it transitions to the real world. Many teams also use an iterative process. They pre-train a policy extensively in simulation where it's cheap and fast, and then they perform a shorter phase of fine-tuning on the actual physical robot using limited real-world data just to adapt the policy to the specific nuances of that particular robot and environment.
That makes sense. Tackling the sim-to-real gap. That brings us to the second big hurdle you mentioned, the fundamental constraints of Adder itself, the hardware and physical limitations.
Yes, absolutely. Beyond the digital challenges of simulation and algorithms, embodied agents are fundamentally constrained by the laws of physics and the current state of hardware technology. These physical limitations directly impact what robots can learn, what they can do, how fast, how long, how reliably. A prime example is dexterity and manipulation. Replicating the sheer dexterity of the human hand, its combination of strength, speed, fine motor control, and rich tactile sensitivity remains one of the grand challenges of robotics. Creating such capable hands is incredibly difficult and very expensive. This is a major bottleneck for robots performing complex manipulation tasks, which are essential for many proposed applications. Then there's power and efficiency. We touched on this, but for untethered robots, battery life is a constant nagging concern. High-torque motors, powerful onboard computers needed for running the AI models, a full suite of active sensors, these things consume a lot of power. They can drain a battery in just a few hours, severely limiting operational uptime and practicality for tasks requiring a full workday. And lastly, but crucially, durability and reliability. Robots operating out in unstructured real-world environments, factories, warehouses, outdoors, homes, must be able to withstand collisions, wear and tear, environmental stressors like dust and moisture. Designing and manufacturing robots that are both highly complex mechanically and electronically and highly reliable over thousands of hours of operation is a significant engineering feat and a major driver of their current high costs.
So even if the software gets incredibly smart, the physical body itself presents these massive engineering and cost challenges. And the third hurdle you raised, the quest for generality, that sounds like maybe the most profound, the most AI challenge of them all.
It is, in many ways. The ultimate long-term goal of much of the embodied AI research is to create agents that can perform a wide variety of tasks across diverse, unstructured environments, much like humans can. But current systems, even the most advanced ones, are still very far from this ideal of general-purpose competence. It turns out to be exceedingly difficult for an agent trained on a specific set of tasks and objects, even thousands of them, to truly generalize its knowledge to new, previously unseen situations. A robot that learns to perfectly pick up a specific blue block from its training set might completely fail when presented with a red cup, a tool it hasn't seen before, or even a crumpled piece of paper. It highlights this fundamental gap between narrow intelligence, which excels at a single task or a narrow range of tasks, and general intelligence, which can flexibly apply knowledge across different domains. And this difficulty is compounded by what's often called the long tail problem. This refers to the fact that the real world contains an almost infinite number of rare, unexpected events and situations. It's simply impossible to pre-program or train a robot for every conceivable rare event it might encounter. True autonomy seems to require not just pattern matching from training data, but the ability to handle novel, unforeseen circumstances using common sense reasoning and robust problem-solving skills.
So these three hurdles, the sim-to-real gap, the hardware limitations, and this quest for generalization, they're all tightly connected, feeding into each other.
Yes, exactly. They form this challenging feedback loop, this trilemma. To achieve true generalization, robots need vast amounts of diverse data, ideally from real-world interactions. But hardware limitations like cost, battery life, and durability make collecting this massive amount of real-world data incredibly slow and expensive. This forces a heavy reliance on simulation to get the necessary scale of data, which in turn introduces the sim-to-real gap we just discussed. And even highly realistic simulations struggle to capture the full complexity and, crucially, that long tail of rare events found in the real world, which is exactly what's needed for true generalization. So breaking this cycle, finding ways to get more generalizable learning from less real-world data, or making simulation transfer more reliable, or making hardware cheaper and more robust, that's really the central task for the next generation of embodied AI research and development.
Okay, we've walked through the fundamentals, the history, the intricate anatomy, the applications, and these significant hurdles. But despite those challenges, the long-term vision for embodied AI remains incredibly ambitious. What does the horizon look like? What's the ultimate goal here?
Well, the ultimate goal animating much of the research and the massive investment we're seeing is the creation of truly autonomous general-purpose robots. The vision is for machines that can eventually perform a vast range of physical tasks, operating effectively in complex human-centric environments. Think about robots seamlessly transitioning from assisting on a factory assembly line to loading a dishwasher in a home, providing physical assistance for elder care, or performing routine maintenance tasks. Some experts project that, if the current pace continues, billions of such robots could potentially be operating globally by around 2040, fundamentally transforming sectors ranging from healthcare and logistics to retail, hospitality, and personal assistance in the home.
Billions by 2040.
Yeah.
Staggering number. What are the critical milestones we need to hit to even approach that kind of future?
We need significant breakthroughs on several fronts. We absolutely need to effectively bridge that sim-to-real gap, making virtual training reliably transferable to physical deployment. That's key for scaling learning. We need to achieve robust generalization so robots can handle novel tasks in unstructured environments safely and effectively, not just the specific things they were trained on. And we need continued innovation in hardware engineering, developing next-generation actuators, sensors, and power systems that can deliver human-level dexterity, perception, and endurance, but critically, at an affordable cost point. Mass adoption won't happen if each robot costs as much as a luxury car. One particularly promising frontier, especially for robots intended for close human interaction, is soft robotics. By constructing robots, or at least key parts of them, from compliant, flexible materials, researchers aim for machines that are inherently safer for physical contact. A soft robotic arm, for instance, is intrinsically far less likely to cause injury during an unexpected collision than a traditional rigid metal one. This is a crucial consideration for applications like in-home caretaking or collaborative manufacturing.
This sounds like it could trigger a massive economic and labor market transformation. Is the primary story going to be about job displacement? Or is it more complex?
It's definitely more complex than just displacement. It's likely to be a duality of displacement and creation. There's no doubt that advanced robots, particularly embodied ones capable of physical tasks, will automate many jobs that are currently performed by humans, especially those involving repetitive, predictable, or physically strenuous manual labor. Sectors like manufacturing, warehousing, logistics, even agriculture and construction are likely at the forefront here. Job displacement in these areas is an unavoidable consequence of this technology. Some macroeconomic projections, like one from the McKinsey Global Institute, suggest that automation, including robotics, could impact up to 800 million jobs worldwide by 2030, requiring workforce transitions. However, history shows that technological revolutions also create entirely new industries and job roles. The same wave of embodied AI is expected to generate significant demand for workers in robot design, development, manufacturing, deployment, training, supervision, and maintenance. And as robots take over certain tasks, new human-centric roles will likely emerge, focusing on tasks that require creativity, critical thinking, complex problem-solving, and social intelligence skills that remain uniquely human, at least for the foreseeable future. The focus might shift to humans managing fleets of robots or collaborating with them on more complex tasks.
So the key then is managing that workforce transition and preparing people for these new roles.
Exactly. Navigating this massive shift successfully requires proactive, large-scale societal investment in education, reskilling, and upskilling programs. The goal must be to prepare the workforce for future jobs that are complementary to automation rather than in direct competition with it. This is a major challenge for governments, educational institutions, and industries. Simultaneously, embodied AI is enabling new business models that could actually democratize access to automation. The rise of robot as a service, or RIAS, is a key trend here. Instead of buying expensive robots outright, companies can lease robotic capabilities on a subscription basis. This significantly lowers the large upfront capital investment traditionally required for automation, potentially allowing even small and medium-sized enterprises, SMEs, to adopt the technology, improve their productivity, and enhance their competitiveness.
Okay, when we start talking about billions of autonomous robots interacting in the real world, sharing spaces with us, safety and accountability become absolutely paramount concerns. How are those fundamental challenges being addressed?
They are, or certainly should be, top priorities. Safety is the foremost ethical imperative. Unlike a software bug, a mistake by a powerful physical robot can have immediate, potentially devastating, and irreversible consequences in the real world. So, safety engineering for robotics involves multi-layered approaches. This includes things like redundant sensor systems so the robot doesn't lose perception if one sensor fails, fail-safe mechanisms built into the actuators so they default to a safe state if power is lost, and sophisticated control algorithms designed to guarantee predictable, safe behavior, especially when operating in close proximity to humans. Then there's the very tricky issue of the accountability gap. When an autonomous robot makes a mistake that causes harm, property damage, injury, or worse, who is legally and morally responsible? Is it the owner who deployed it, the manufacturer who built it, the company that wrote the AI software, the specific engineer who worked on a particular algorithm? The very autonomy that makes these systems powerful also makes tracing a clear chain of causality incredibly difficult. Addressing this requires a combination of technical solutions, like developing more interpretable and explainable AI models so we can understand why a robot made a certain decision, and implementing comprehensive logging of sensor data and internal states to provide an evidentiary record. It also requires regulatory solutions. We're starting to see new legal frameworks emerge, like the European Union's AI Act, which aims to establish liability standards for high-risk AI systems, including many types of robots. And it's also crucial to consider how algorithmic bias, which we know exists in software AI, can manifest in potentially dangerous ways in a physical robot. For example, if a robot's perception system is trained on data that isn't representative of the population it will interact with, it might perform less reliably or less safely around certain demographic groups. A facial recognition system less accurate for darker skin tones could lead to improper or even unsafe interactions. Rigorous testing using diverse representative data and active bias mitigation techniques are absolutely crucial to ensure equitable and safe performance for everyone.
And beyond the technical and legal aspects, what about the social fabric itself? How will widespread interaction with capable robots redefine our relationships, our communities, our sense of self?
This is perhaps the most profound and maybe the least predictable long-term impact. For robots to coexist successfully and productively with humans, especially in shared public spaces or homes, they need to do more than just follow programmed rules. They will eventually need to understand and adhere to our complex, often implicit social norms and expectations. This requires a level of sophisticated social intelligence that is far beyond current capabilities. The field of human-robot interaction, or HRI, is dedicated specifically to designing interactions that feel natural, intuitive, and fluent for humans. A central challenge within HRI is building calibrated trust. Humans need to trust a robot enough to work with it effectively and comfortably. But over-trusting a system's capabilities, assuming it's smarter or more aware than it really is, can lead to dangerous situations. Researchers are exploring how to design robots that are more transparent about their limitations and uncertainties, allowing humans to form an accurate mental model of what the robot can and cannot reliably do. This is essential for fostering a healthy, safe, and productive collaborative relationship. And then there are the complex dynamics around emotional and social bonds. Research consistently shows that humans, particularly children and the elderly, can form genuine emotional attachments to social robots, even relatively simple ones. This presents a tremendous opportunity, for instance, using robots to alleviate loneliness and social isolation, which is a major public health issue, especially for aging populations. But it also raises significant ethical concerns about the potential for emotional manipulation, unhealthy overdependence, or even the replacement of essential human contact, especially for vulnerable populations. Designing robots that can provide companionship and support without creating unhealthy attachments or eroding human relationships is a really crucial and delicate ethical frontier we're just beginning to navigate.
This has been an incredibly insightful deep dive. It's absolutely clear that this embodiment revolution marks a really pivotal moment in the history of AI. It's a powerful return
in many ways to AI's earliest cybernetic roots, but now supercharged by incredibly advanced AI techniques, much more sophisticated hardware, and frankly, massive investment. Creating a truly capable embodied agent is just a monumental undertaking, isn't it? Blending these physical bodies with complex digital minds built on layers of reinforcement learning, world models, multimodal AI, and maybe these overarching cognitive architectures.
It really is. And while the path forward is definitely still laden with those significant hurdles we discussed, that stubborn sim-to-real gap, the very real physical limitations of hardware, and that grand challenge of achieving true generalization, the progress, especially recently, is undeniable and seems to be accelerating. A new generation of humanoid robots from companies like Tesla, Boston Dynamics, Figure AI, Sanctuary, Agility, and others are demonstrating capabilities that honestly felt like science fiction just a few short years ago. These agents are beginning to find real-world applications, starting to optimize structured environments in logistics and manufacturing, while simultaneously taking their first steps into the far more complex and unstructured worlds of healthcare, scientific discovery, and potentially, eventually, our daily lives.
So as these intelligent machines continue to move, quite literally, from the factory floor potentially into our homes and communities, reshaping industries and our daily interactions, maybe the deepest question isn't just what they can do for us or even to us. Perhaps it's who they will become and how we, as a society, will choose to define our shared future, when intelligence is no longer confined primarily to the digital realm, but actually walks among us.